Good morning. All right. Today we are covering fatigue and bioenergetics as they relate to endurance performance. I've got a lot of material to cover, and as I promised you guys, I am going to try to adopt my less is more approach. So some of the slides you will see me move pretty quickly. If I say don't worry about something, it means just that. Don't worry about a specific point. If I spend more time on a specific point, clearly you guys should be taking more notes on that specific topic. So for an overview, we're going to start by just discussing performance in a very general sense and how it relates to fatigue. From there, we'll move into bioenergetics. We're going to spend a decent amount of time talking about the glycolytic and the oxidative systems, because especially the oxidative system is relevant to endurance performance. Then we're going to connect these energy systems and see how they relate to exercise. And then finally, the most important thing is how do these energetic systems with regards to exercise, how can we manipulate them to maximize or improve performance? So let's jump in. So, as a coach, physiologist, strength sports scientist, whatever you want to call it, our goal is to optimize performance. So typically, if we were live, what I would ask you is, well, what factors are related to performance? And what you guys should do is pause this video. Think about it. Pause this video right now and see if you could list 10 factors related to performance. Take a few minutes. All right. Having said that, here's just a few that I rattled off pretty quickly when putting together this presentation. It could be endurance, it could be top end speed, it could be technique and efficiency, nutrition, acceleration, whatever it is. In a very, very simple sense, all of these has some sort of endurance component, right? How long can we maintain our power production? How long can we continue? How long can we continue to improve our rate of force development? Nutrition. How long can we maintain a specific nutritional lifestyle? Whatever it is. In a very simple sense, each of these has an endurance-oriented component. So, knowing that, let's start with some basic definitions. Endurance, right? How do we define endurance? Right? So endurance can be defined as the ability to resist fatigue and maintain production. I specifically highlighted fatigue as, again, this is very relevant for us in this class. So what's production? Well, production in our cases when working with athletes could be running velocity, swimming velocity, it could be repetitions in the gym, or perhaps even in the workplace. In the workplace, we do develop fatigue, and our production or efficiency in the workplace will sometimes decrease. So I specifically highlighted fatigue, right? That's our segue to our next slide, right? What is a definition of fatigue? Once again, pause this slide, think about it. What is a good definition for fatigue? Write it down. Well, a lot going on this slide, right? So Abyss and Lorson put together a very thorough review on different fatigue models, right? But, right, they did start with a simple definition. A simple definition of fatigue is a sensation of tiredness associated with overall decrements in performance and function, right? So it's just this tiredness, and because of this tiredness, there's a decrease in function, right? I am going to actually read this entire quote. This quote comes directly from my master's thesis, right? Again, my master's thesis was on triathletes and endurance performance, so it fits perfectly with where we are. It is generally accepted that there are two areas of fatigue, central and peripheral. Central fatigue includes models associated with the brain and spinal cord, while peripheral includes all other systems extending beyond the spine, specifically cardiovascular, nervous, and muscular. Within both areas of fatigue, numerous models have been built. It is beyond the scope of this review to discuss every model, but to illustrate the point, within their review on fatigue and cycling, Abyss and Lorson discussed 8 different models that may affect performance. So these two authors came up with 8 different models to affect why someone might actually slow down while cycling, because this was based on cyclists. I've specifically highlighted the cardiovascular slash anaerobic model and the energy supply and depletion model. I think those are the most commonly utilized, and obviously the energy supply and depletion model is going to fit nicely with what we're talking about today. One of your reading assignments for the following week is going to read this article, only the section, the introduction and the sections on the cardiovascular and energy supply and depletion model. There will be some questions next week on these sections. So, bioenergetics. Well, simply, let's break it down. What is bioenergetics? Bioenergetics sounds like a really fancy term, but it's not. Biology, right? Bio, study, the science or study of a living organism. And energetics is simply energy. So it's the study of the transformation of molecules to produce energy. We're trying to see how our human body, right, a living organism, transforms molecules to produce energy. We as human beings have 3 dominant energy producing systems, and now this is where everything should start to be a review from exercise physiology, right? You've got your phosphocreatine system, your glycolytic system, both fast and slow, and your oxidative system. So before we even jump into the systems, actually, we have to talk about our basic unit of energy. Again, a review, which is ATP, adenosine triphosphate. How does ATP produce energy? Well, we cleave off one of the phosphate molecules, and in that chemical reaction, right, that bond breaking, there's a release of energy, and that leaves us with energy, ADP, right, adenosine diphosphate, and an inorganic phosphate molecule. Okay. So the one that you don't really have to worry about is your phosphocreatine system or your PCR system. This is for explosive activities lasting 10 seconds or less. Very little related to endurance performance. It could be related, you know, in like cycling, if there's like a breakaway in a pack where you have to explode and catch somebody. It could be in like it could be utilized in a sprint finish, or maybe climbing a hill. Your phosphocreatine system can definitely be kind of upregulated in a sense during activity. But for us, we're spending a lot more time focusing on both your glycolytic and oxidative systems. Even your glycolytic system is not going to be utilized heavily for the endurance sports that we're talking about. Okay, so your glycolytic system is going to be really lasting up to 3 or 4 minutes, right? And we're talking about usually, at least for your training program at the end of the semester, you have to write things for people running a 5K or longer, half marathon, marathon, Ironman type events. But this is to give you some basic understanding of your energy systems. So glycolysis, right? Again, I try to help you guys with just definitions. Lysis means breakdowns, whether it's glycolysis or lipolysis. Lysis means breakdown if it's at the end. Okay, so it's the breakdown of glycogen, right? We need to utilize for energy, we need to break glycogen down into glucose, right? Glycogen is the storage form in our body of glucose. So we have to break that down first to glucose before we can utilize it in the remaining energy systems, which would be the Krebs and the Krebs cycle and the electron transport system. So once we get to glucose, right, after it goes through all of its chemical reactions in glycolysis, this should leave us with ATP and hydrogen ions plus lactate. All right, I wanted to put this in here just so we're clear about what produces that burning sensation, right? What really causes fatigue? Well, one possible element of fatigue, remember, Lorson and Abyss wrote about 8 different models. One possible mechanism of fatigue is an accumulation of hydrogen ions, right? And this can possibly prevent our muscles from contracting because of this accumulation. Listed here at the bottom is essentially the bioenergetic pathway that glucose follows. We do need to understand a few things from this. Right? So glucose eventually gets converted to pyruvic acid or pyruvate, which will eventually get converted to acetyl coenzyme A. Acetyl coenzyme A or acetyl CoA is the major product we need, whether it's glucose as our starting substrate or whether it's triglycerides as our starting substrate. They both need to come and eventually become acetyl CoA before they can enter the Krebs cycle or electron transport system. Now, for glucose, right, once it goes through glycolysis, it produces about 30 to 38 molecules of ATP. Now, I say about because it really depends on the source that you're reading. Because some people I've even seen as little as 28 molecules of ATP. Some, like your CSCS textbook that a lot of you had from my last class, that says 40 molecules of ATP. It really depends where your source is, but you could say in the neighborhood of 30 to 38 molecules of ATP. Oh, and then obviously this takes a little bit longer to do than your phosphocreatine system. Glycolysis continued. So I already wrote glycolysis is the breakdown of glucose or glycogen. Some other key things that we need to note is that oxygen, is it required? Yes and no. We've talked about it being fast and slow. For the initial reactions, no, but if it does need to enter the electron transport chain, then yes, oxygen is required. So if that is a question on a quiz, the answer could be, depending on how it's yes and no. So an important hormone, right, is GLUT4, right? GLUT4 is a transporter hormone involved in glycolysis to utilize glucose for energy. What GLUT4 does is when it's needed, right, it migrates, right, to the edge of the cell membrane. So it starts more towards the center of the cell, and as its energy is needed, it migrates to the edge of the cell. Once it gets to the edge of the cell, it helps transport glucose into the cell so it can get to the mitochondria for energy. What we know is that GLUT4 is upregulated during and after exercise. We also know that GLUT4 is sometimes upregulated from eating very sugary meals or sugary snacks. Okay, so this is important, right? If we need glucose for energy, we want GLUT4 to go to the edge of the cell. So GLUT4 is very important. It's one of the reasons, at least in theory, why some people believe that post-workout you should have a sugary snack, and that's because we want to upregulate GLUT4, or at least GLUT4 action, right? So if GLUT4, by having a sugary snack, will be closer to the cell membrane, this could, in theory, help replenish muscle glycogen after a big workout. So if somebody's doing double sessions, I'll often tell them right away, get some type of sugary snack so we can help replenish muscle glycogen so you can come back later and exercise at an equal or even better intensity in the second session. So this is a key. If you start with glucose as your starting substrate, and this is again why some of the numbers will vary, glucose produces a net yield of 2 ATP versus glycogen, which produces a net yield of 3 ATP. So your starting substrate will actually influence your final ATP count. It's another reason why that range is like 28 to 40. I wrote 30 to 38 ATP. So moving on to your oxidative system. This is the big one, right? So pretty much anything lasting over 4 to 5 minutes is going to primarily utilize your oxidative system for energy, right? This is where O2, right? It's aerobic. It requires oxygen to produce energy. Our starting substrates are triglycerides. This reaction produces the most amount of ATP. Remember that. That is incredibly important for what we're discussing next, right? So the oxidative system and or fatty acid oxidation produces the most amount of ATP. Remember that. However, it does take the most amount of time to produce that ATP. So these chemical reactions take a little bit longer than the glycolytic system and much longer than the phosphocreatine system. So, right, we're talking about the oxidative system, so we obviously have to start to discuss fat. For our purposes, we are going to consider fat a triglyceride. Um, this is not the full definition of fat, because fat, in terms of your diet, can also include cholesterol. But for our purposes, we are going to simply use fat and triglyceride in this case interchangeably. Fat exists within our body, both within our adipose tissue, right, within our muscle cells in the form of an intramuscular triglyceride, and in our bloodstream. Okay. Your goal, as I stated earlier, right, clearly this is important, is we need to get our starting substrate, in this case fat or a triglyceride, to acetyl coenzyme A before it enters the Krebs cycle. Right, so we have to break it down. How do we break down triglycerides? Right, well, a triglyceride, right, is one glycerol molecule combined or bound to 3 fatty acids. Right, so triglyceride is one glycerol combined with 3 fatty acids. All right, in order to break down that starting compounds, you need a hormone known as hormone-sensitive lipase. Hormone-sensitive lipase, what it does is it cleaves off your glycerol molecule, and then it leaves you with the 3 triglycerides, right? Three fatty acids, right? So 3 fatty acids plus glycerol after hormone-sensitive lipase breaks that down, right? From here, we've now got our 3 fatty acids, but how do we utilize them for energy? Well, we need to get them to the muscle, right? That we need to get them to the muscle so the muscle can find energy to contract. Right? So we're talking about initially being within a fat cell or an adipose cell. Now we need to transport it to the muscle via albumin, right? Albumin is going to help transport those fatty acids to the muscle. Once it gets to the muscle, right, the fatty acid gets into a form of what's called, I think it's a fatty acid acetyl coenzyme A, and then fatty acid acetyl coenzyme A gets transported in the muscle to the mitochondria via carnitine, right? Carnitine acyl transferase, right? Once it enters the mitochondria, it can finally undergo beta oxidation, which you guys should all remember from exercise physiology. All right. And then finally a graphic, right? Finally a graphic. So for the purposes of this class and most exercise science textbooks, we largely ignore breaking down protein for energy, right? For the most part, we spend a lot of our focus on glycogen and triglycerides, but it's always important to remember that protein can be utilized for energy, especially in endurance sports. We've seen it utilize up to 10 or 15% of energy. However, depending on exercise intensity, the vast majority of energy comes from both those glycolytic and oxidative systems. So this is really just to help reinforce some of the things that we just talked about, where glycogen, if we're looking down the middle, glycogen gets broken down into glucose. It undergoes glycolysis, right? So remember, glycogen it absolutely must be broken down into glucose or some monosaccharide, well, glycogen in this case glucose, but we can utilize other monosaccharides for energy like fructose. From glucose, then we can finally begin the process of a glycolysis. Glycolysis converts the glucose into pyruvate, and then pyruvate, like I said, the kind of the golden substrate that we need before the Krebs cycle is acetyl coenzyme A, right? Then it enters the Krebs cycle and then finishes off with ATP. Now, if you look to the right, very similar, where we have our triglyceride, like I just spoke about, gets converted into our fatty acids, and our fatty acids eventually get converted also into acetyl coenzyme A before it enters the Krebs cycle. Right, so you guys can see how important acetyl coenzyme A is as our what I'll call our intermediary substrate for entering the Krebs cycle. All right, moving along. So this is an activity I would usually do. I would usually kind of just pull two people up on the board and have them draw what they think would be energetic contributions to exercise. So we have a few things we have to remember, right? While we are working out, while we're sitting down, while we're doing everything that we're doing, energy contributions, right, to exercise always exist on a spectrum. There is never one system that is 100% turned on and the other systems being 100% turned off. Okay? All systems are running, but at different percentages. Once we know that, the question really becomes, well, how do we maximize performance? Which system do we want on? Or which system do we want mostly contributing to energy? Do we want mostly carbohydrates? Do we want mostly fat? What currently are we relying on? And inevitably, can we shift that system to what we want it to be? Right? This is what upregulation is. Okay? So I drew on the next slide a very, very crude graphic. I made this in about 5 minutes when putting this set of slides together. Normally I would draw this on a whiteboard in front of all of you guys. So the graphs are similar. We'll look at the left one first. On the x-axis, we're talking about exercise intensity. In this case, we'll talk percentage of VO2 max, right? On the y-axis, we've got our relative contributions of energy, so it's all relative. So the highest contribution of energy is 100%. The lowest would be 0%. But remember, something is always on, so neither of these are ever at 100%. So this line right here on the left, we start, if we're at a very low exercise intensity, maybe we'll say, I don't know, 20% VO2 max, 15% VO2 max, right? Carbohydrate contribution is extremely low, right? Maybe this is 10%, and fat contribution for energy might be 90%. As exercise intensity increases, right? So as we go along the x-axis, clearly you can see the contribution of energy starts to increase from carbohydrates and decrease from fats. At a specific exercise intensity, in this case 50% VO2 max for this individual, right? We're at approximately 50% carbohydrate, 50% fat contribution of energy. And then obviously, as exercise intensity increases, maybe let's say this is 90% VO2 max, we are relying heavily on carbohydrates for energy and very much less so fat. Now, in theory, there are some possible benefits to being more what we would call fat reliant. Okay, so in theory, if there's some possible benefits, a question is, can we shift this graph to be more reliant on fat for energy at higher exercise intensities? Okay, so if you're following, right, this graph is very similar, right? The only thing is that at a higher exercise intensity, right, we're actually utilizing more fat. So at 60% VO2 max might be where our crossover is now. And this actually happens. This is a very crude graphic and these numbers are fictitious. But we have seen individuals that can change their utilization of energy to be more reliant on fat instead of carbohydrates, and vice versa, depending on a few different variables, not just one or two. You guys will see that next. So now we're starting to think in terms of performance. Well, what limits endurance performance? Well, we talked about substrate availability and energy availability. Clearly, that's what we're focusing on today, right? So, so the substrate theory simply states that there's just not enough ATP for the muscles to contract, so the contractions have to produce less force, or in practical application, we have to slow down, right? So there's some theory for utilizing, like I said, fat as a preferred energy source for exercise intensity. We know that fat oxidation produces much more ATP than carbohydrate or glucose, through the process of glycolysis. Okay, so there's a higher energy yield, right? In this case, what I wrote is 38. I used the number 38 ATP for glycolysis versus 130 ATP for the oxidative system. That's a massive difference. So fat, right? One molecule of fat is going to produce nearly 100 more ATP than one molecule of glucose. Massive. I mean, so in theory, we should want to utilize fat for energy. Again, this was exactly what my master's thesis was on. Right? In addition, right, there's some other cons of carbohydrates. We all know from exercise physiology and body composition, or just from dieting, that eating more carbohydrates, right, they make you heavier, right? Carbohydrates retain water, right? They retain H2O, and that water is going to make you heavier. And it might only be 2, 3, 5 pounds, but a 5-pound difference over the course of an event like a marathon, or swimming, doing a 3-mile swim, or a 110-mile bike ride, is going to make a massive difference in your overall time. So that's another con of being more carb reliant. And this is probably the biggest benefit of utilizing fat and being more reliant on fat, and that is total substrate storage, right? So stick with me, I'm going to continue to expand on this. In order to complete an Ironman, it costs us about between 8 and 12,000 calories of energy. So in order to complete an Ironman, for those of you that don't know what an Ironman is, an Ironman is kind of the golden triathlon, so to speak, right? It's the longest triathlon, and there's dozens of them around the world at this point. But these contests start with a swim of a 2.4 mile swim, followed by, right, immediately into a 112-mile bike ride. And then immediately after that, you run a marathon, right? 26.2 miles. So this is all back to back to back. Your average time to complete a Ironman triathlon for the elites is somewhere about 8 to 9 hours. Your average time for your average competitor is probably about 11 hours, give or take, 12 hours, give or take, something along those lines. So you'll see people pretty much working out all day, right? And this utilizes about, during this process, between 8 and 12,000 calories of energy. So here's the problem. In terms of carbohydrates, we only hold as humans, right, 1,800 calories, 450 grams or 1,800 calories. So we only have 1,800 calories, but we need about 10,000 to finish an Ironman. So the only way you're going to finish an Ironman, if you're much more reliant on carbs, is by refueling, and refueling extremely often during an Ironman triathlon. But the human body, even the leanest individuals, are going to hold at least 10 times more fat for energy. So this is an author, Jukendrup. He's big into sports nutrition, right? So for the average person, with carbohydrates in the neighborhood of 450 grams, our average exercise time, right, the availability that we can use this time is going to be about 100 minutes before we need to refuel. Okay, that's for carbohydrates. For fat, the average time we can exercise before we need to refuel, if we're reliant predominantly on fat, is 4,900 minutes, right? So that's a massive difference, right? If you think about that and you look at it, right, you're going to be able to do a full Ironman without really refueling if you utilize mostly fat for energy. So this is a big time benefit, right, of using fat for energy. And we started to understand this in probably the mid 80s, 90s, or realize this, and we really started to test this in the research in the mid 90s and early 2000s. Slide looks a little off. So it had been tested a lot in the mid 90s and early 2000s. I also tested it for my master's thesis. But we're starting to see that there's some rate limiting factors of fat oxidation, right? Um, so one thing that slows us down is that lipolysis or breakdown of fat in adipose tissue is one of the limiters of performance. It just takes too long, right? So while we have this almost limitless supply of fat for energy, it just takes too long to actually go through the entire process of breaking it down. The availability and the rate to break down triglycerides in the muscle cell is another factor that's going to limit performance. Where intramuscular triglycerides, remember I said we have our adipose tissue, but also within our muscles, right? Pointing to my bicep here, my quadricep, we just don't have enough within our muscle cells. So intramuscular triglyceride stores are low, and that's also going to limit performance. And then finally, something that might also limit performance, right, is transporting fatty acids across cell membranes. And one of those substances, I don't know if it was in this slide, is going to be carnitine. Yeah, we talked about carnitine. So how do we burn more fat for energy, right? How do we upregulate fat oxidation? Well, there's several methods, as I stated earlier. The first method is simply by going through endurance training. Through endurance training, several physiological changes take place, right? One, we're going to improve our capillary density within our body, right? If we improve our capillary density, right, we're going to be able to improve our blood flow to our working muscles. And if we can improve our blood flow to our working muscles, right, well, what did we just say with fat? Well, we're transporting our fatty acids through the protein carrier albumin. If we can get those fatty acids to the muscles better or faster through improved capillary density, we can increase the rate of chemical reactions, right? Two, all of these so the Krebs cycle and beta oxidation, they all take place within the mitochondria. Okay, through endurance training, we actually increase our mitochondrial density. So if we have more mitochondria, we should be able to go through an improved rate of beta oxidation. We have also seen, I already stated that one limiting factor of fat oxidation is intramuscular triglyceride storage. Well, by endurance training, we actually might be able to store a little bit more within our muscles. Next, so other than just training, there's a few other what we'll call body hacks. Caffeine. Caffeine has been shown to upregulate fat oxidation. Supplementing with L-carnitine. This in theory seems to make sense. Some research does show that this works, some not so much, but it makes sense because we already said in order to transport it's the fatty acid acetyl-CoA to the mitochondria, we need that transport carrier, and L-carnitine is part of it. Supplementing with medium chain and long chain triglycerides. So you guys have probably seen this in some of these I don't know, these like coffees that swear that they upregulate fat oxidation. So like by drinking certain coffees, that have medium chain triglycerides in them. It's supposed to upregulate fat oxidation. The research is conflicting on that. And then the last, and I think the most important thing, is fasting, right? By simply fasting or lowering carbohydrate intake, right? There's less carbohydrates available, so we can, if there's less carbohydrates available, we have to become much more reliant on fat for energy. So to wrap this up, I think this is our last slide. The question really is, does a high fat, low carbohydrate diet work? Does it work for performance? Well, so these are all findings from my master's thesis, and based on other research. What we found is that long chain triglycerides supplementation doesn't seem to improve endurance performance. Fasting doesn't seem to improve endurance performance. So fasting probably doesn't improve endurance performance because we still need calories for other things and other processes. So fasting doesn't really seem to work. Now, lowering your carbohydrate stores might be a different story. All right, supplementing with carnitine. Again, there's conflicting research. It might help, but I found that based on the body of evidence, it doesn't really seem to improve endurance performance. Now, what does work? Well, medium chain triglyceride supplementation might actually help. So that's something to consider. A high-fat diet, 3 to 7 days, impairs moderate intensity and runtime to exhaustion in untrained men. So this is just simply a quote. I forget if this was from another study or mine, honestly, but a high-fat, low-carbohydrate diet is actually going to impair moderate or greater exercise intensity, so you probably don't want to do it for that. So, and this is your final quote that you're left with. At the present, there is insufficient evidence to recommend that athletes fat load or go with a low carb, high fat diet in order to upregulate fat oxidation before competitions. However, in my opinion, I think it's possible for super long endurance events, ultra endurance events, things that are 6 hours or longer, that a high fat, low carbohydrate diet might work. So for something like a 5K, you might hear people talking about this. Honestly, it's pretty common in the endurance sports world. They talk about like being quote unquote fat adapted. For something like a 5K, being a fat adapted absolutely means nothing. Now, when you get up to an event like a half marathon, it probably still means nothing. And I strongly believe being fat adapted means very little for a half marathon. When you get to a marathon, maybe at the higher level, people that are running marathons at, the 2-hour 15, 2-hour 20-minute mark for males, and like the 2-hour 40-minute mark, 2-hour 45-minute mark for females, maybe it might have some effect. But in reality, we really need to be in the greater than 6-hour window where it might have an improvement on performance. All right, that is it for your first lecture. Hopefully you guys took some notes. If you guys have any questions, shoot me an email.